Welcome to Topic 6.5, Statistical Design and Planning, Association, Causation, and Bias. By the end of this topic, we hope that you'll be able to determine the differences in association between exposure and outcome and a causal relationship between exposure and outcome. You'll be able to apply the stages of assessing an association for causality and know how to control for bias and confounding in study planning and analysis. Finally, you'll understand how to prioritize and apply criteria for causal inference. In Topic 6.3, we covered the basics of analytic epidemiology, of which the goal is to understand, are the exposure, or risk, and the disease, or outcome, linked? To do this, we have to identify and quantify the relationship between the exposure and outcome. In statistical terms, our exposure variable is the independent variable, and the outcome or disease measure is the dependent variable because we think that it depends on the exposure. That is, that the exposure to the risk factor is causing, in some part, the health outcome. Finding an association means that there is an identifiable relationship between an exposure and disease. The exposure might cause the disease or outcome. Causation implies that there is a true, measurable mechanism that leads from exposure to disease. Finding an association does not make it a causal relationship. Returning to our cigarette smoking example, we first have to identify what we think the relationship might be. Is cigarette smoking associated with lung cancer? Find that an association exists through statistical hypothesis testing, as we'll cover in 6.6. Cigarette smoking is associated with lung cancer. And quantify the strength of that relationship, which will provide greater evidence for a causal argument, such as finding that smoking 50 cigarettes a day is associated with a 27 times higher odds of lung cancer than smoking 0 cigarettes a day. As mentioned before, you need to have at least 2 groups to evaluate an association, one of which is a comparison group that does not have either the exposure or the disease outcome in question, depending on your study design. We get a statistical association between an exposure and disease, and we want to know whether the association is causal. For the exposure to be a cause of a disease, it must precede the disease event, and without it, the disease would not have occurred. The basic scenarios of causality are that 1, there is no association between the 2 variables, 2, that A causes B, and 3, that B causes A. But in reality, a model of disease causation really looks more like this, in which multiple levels of factors are in the causal pathway for a disease outcome. We can measure factors on all of these levels and look for an association, but we have to choose one independent variable to begin with. In this model, you might start with obesity as the exposure and diabetes as the outcome, with the knowledge that there are many factors that contribute to the development of obesity and its relationship to diabetes. You can do complex modeling and measurement to reflect this, but you have to start with the most immediate, potentially causal relationship. Once we determine that an exposure is associated with a health outcome, evaluating whether an association reflects a causal relationship happens in 2 stages. In stage 1, we ask ourselves whether the association can be due to bias, confounding, or chance, rather than to the exposure-disease relationship we've measured. If we find that the association is unlikely to be due to bias, confounding, or chance, we move to stage 2, in which we apply guidelines for causal inference. This model reflects the order in which this 2-stage process occurs, first assessing primarily for selection or information bias, then confounding bias, and then chance or error. We cannot say with absolute certainty that an association is not due to chance, but we can determine the probability that it is not due to chance. Then we apply the set of causal guidelines. The first possible alternate explanation for the association that we can investigate is bias. Is the association we found likely due to bias? Bias results from error, and there are two types of error we encounter in our studies. Random error, which is the divergence due to chance alone of an observation on our sample from the true population value, which leads to a lack of precision in the measurement of our association. Systematic error is an error that's not determined by chance, but is introduced by some inaccuracy inherent in the system. And we have more control over systematic error than we do random error. Bias is this systematic error in the design or conduct of our study that results in a conclusion that's different from the truth. And this can happen at any stage of inference, which produces values that depart systematically from the true values. So this can happen during design, data collection, analysis, and interpretation, and we need to make sure that we quantify the presence, the magnitude, and the direction of bias. Most commonly, bias occurs by the way participants are brought into or leave a study, or selection bias, or when the information that we obtain from studied participants is systematically inaccurate, which is measurement or information bias. Selection bias refers to this systematic error that arises from procedures used to select study subjects or factors that influence study participation. And then we see that the association between the exposure and the disease or outcome differs between those who participate and those who don't. And this can happen when there are differences in characteristics between those who are selected or aren't, and that's response bias, selection bias, self-selection bias, and control selection bias, or from differential loss to follow-up in a cohort study like we spoke about, or an experiment, which is loss to follow-up bias. So either participants coming into the study or leaving the study contribute to selection bias. Participants or responders may be different than those who do not respond or participate due to bias in recruitment and selection strategies and in self-selection. Volunteer bias can be an issue when volunteers are less likely to engage in high-risk behaviors than non-volunteers. People who choose to participate may do so because they are more worried about an exposure or feel unwell. People who see doctors more regularly are more likely to be diagnosed with a disease than those who don't see a doctor regularly. So you may have a bias in cases being different from the general population. And if you choose to build a cohort, for example, from an employee group, you should know that employed people tend to have lower mortality than the general population, at least in the United States, and that could differ in different areas. And finally, excluding members of a population because of cost, distance, or other factors, or because you believe they are too difficult to engage, can cause bias and is, in some cases, unethical. These aforementioned ways selection can be biased can also contribute to control selection bias, so how you choose a comparison or control group that is not representative of the population that produced the cases, or differential selection, where you unintentionally select cases dependent on exposure status. An example is selecting cases of some disease seen by one physician or one hospital versus many different physicians or a sample of hospitals. And they may have a different exposure status or exposure disease relationship than others. The solution is to be sure to select cases and controls independent of exposure status, and to identify controls from the same population as the cases. You need to avoid this when you design your study. Loss to follow-up bias is the primary issue in cohort studies or experiments. In nearly all large cohort studies, you're going to see original members drop out. If this occurs randomly, so that on average, the people who drop out are similar across those who remain in the group, then there isn't any bias. But usually these characteristics of those who are lost are different than those who stay, resulting in differential loss. When those who are lost to follow-up are different from those who stay for the entire study, you have loss to follow-up bias. Here's an example of a prospective cohort study of smoking and lung cancer. Calculating the relative risk for lung cancer among smokers compared to non-smokers, we get a relative risk of 9. Imagine that this is the true risk of lung cancer in this population. But how might you see people dropping out of this 10-year follow-up study? Do you think smokers or non-smokers might be more likely to drop out? Why? Or people who end up with lung cancer versus those who don't? Take a few minutes to think about this or to discuss. Imagine that we find only 45 smokers that develop lung cancer, and our total number of smokers in the study is reduced to 955. That would mean that half of cases that smoked were lost to follow-up. We would instead believe that our risk of lung cancer in smokers is only 4.7 times greater than the risk in non-smokers. Our results are biased toward the null hypothesis. Now, we might see that all smokers were dropping out of the study at a greater rate than non-smokers. Here we would see we lost 50% of cases that smoked, but also 10% of non-diseased that smoke. We would see less of a bias towards the null in our results, but would still not find the true value of relative risk of 9. To avoid selection bias in your study, use the same criteria for selecting cases and controls. Select them independent of exposure status. Identify controls from the same population as the cases, and invest in resources for recruiting. Be inclusive of the general population as much as your resources allow. Invest in follow-up to obtain high participation rates, and make sure that people are not dropping out due to a changeable condition, particularly if it affects groups differently. And then if you can refer back to our study design topics in 6.2 to 6.4 for more specifics. Measurement bias or information bias is the discrepancy between the true value and measured value that we typically get in a study. Systematic measurement bias can arise because the information we collect is erroneous, and it typically occurs during data collection. Measurement bias could be due to inaccuracies in measurement of subject characteristics, a flawed method of data collection or test, when your study variables are not well defined, the sensitivity or specificity of a test, and may include examples like recalling prior events or exposures, recording or interpreting data, using different data collection methods, and the method or procedure that you use to categorize the exposure and outcome status. Misclassification occurs when individuals are put into the wrong category of exposure or disease status. We are particularly concerned with this type of bias. Exposure misclassification occurs when the exposed subjects are incorrectly classified as unexposed or vice versa. An example may be that a heavy smoker is actually put into a light smoker category. And disease or outcome misclassification occurs when we incorrectly classify diseased as non-diseased or vice versa. For example, a child with stunting is put into a category of those without stunting. Non-differential misclassification, if you see errors about the same in both groups, is random error. The misclassification does not differ between cases and non-cases in exposure or between exposed and non-exposed in outcome. You may also say that sensitivity and specificity for a test are the same for cases and controls or regardless of disease status. Typically, this will bias results towards the null or underestimate your study results or association. In differential misclassification, that is when the information is better in one group than another or more accurate, and this could either over or underestimate your association. When misclassification about exposure differs between cases and non-cases, or outcome differs between exposed and non-exposed, that is when we have differential misclassification, and this may bias results towards or away from the null, either over or underestimating it. And this can happen when sensitivity and specificity of your exposure test differ among cases and controls. Here's an example. Imagine that we have a study of fruit and vegetable consumption and coronary heart disease. We have an objective blood test that can measure the amount of fruits and vegetables patients have consumed. This is a gold standard and can accurately measure consumption and categorize people into high and low consumption. So this would be our true effect or true values. We find that those who have low consumption of fruits and vegetables with coronary heart disease had 3.5 times greater than the odds of having low fruit and vegetable consumption in the control patients who did not have coronary heart disease. And you can see where our true effect lies in relationship to the null value of 1, which is the null value for an odds ratio. Now imagine our self-report of measure of fruit and vegetable consumption is being used in the study. It has 80% sensitivity and 95% specificity, but it doesn't differ whether people have coronary heart disease or don't. Then we're going to have misclassification of exposure that is the same for both cases and controls, which underestimates or bias our results towards the null. This is our random non-differential misclassification. And you can see that the observed effect here that we get is less than the true effect and closer to the null. If we have exposure that is measured by self-report, again, but subjects over-report their fruit and vegetable intake for controls in both cases and controls, but cases with coronary heart disease are not as likely to overestimate their consumption as the controls. The measure has greater sensitivity among cases of CHD than among controls. Then we'll have misclassification that differs between cases and controls, and in this case, it biases the results away from the null, overestimating the effect, where we see the observed effect is greater than the true effect. Another example of recall bias can occur in a case control study when cases are more likely than controls to recall or report prior exposures. An example of this is a case control study of non-prescription drugs during pregnancy and birth anomalies. So cases would be mothers who gave birth to babies with birth anomalies, and controls are mothers who gave birth to babies without birth anomalies. And imagine the exposure is assessed by asking mothers, what non-prescription drugs did you use during pregnancy? Do you think it's possible that mothers could recall exposure first inaccurately across all cases and controls? And do you think cases and controls could differ in recalling the exposure? Why? And if you could take a moment to think about or discuss this. Mismeasurement of exposure status is present in almost all studies because methods to ascertain exposure are imperfect. There are many ways in which measurement error can occur, and these are some examples for your reference. When exposure or outcome are self-reported measures or are observed by an interviewer, there's opportunity for bias in how individuals recall exposures, and interviewers might interview participants differently if they know which study group that they're in. Similarly, having a subjective measure of an outcome can lead to bias as well. Again, your best opportunity to reduce bias in your study is in your design and planning. Measurement bias can be reduced by using objective markers of your exposure, training interviewers and observers to obtain data in the same fashion for all participants, or blind them to study status. Using standard tools for data collection and definitions for exposure and outcome, and making sure the sensitivity and specificity of your tests are the same across groups. And remember these methods for reducing selection bias. Now that we've evaluated our study for potential bias, we turn to the next question. Is the association we've found likely due to confounding? Confounding is a mixing of effects when the true association between exposure and disease is distorted because there's another factor playing a role that is associated with the exposure and disease. We can think of it as an alternative explanation for an observed association between exposure and disease. You can assess whether your variable is a confounder with 3 criteria. 1, it is associated with the exposure in the population. 2, it is an independent cause or predictor of the disease, at least among the non-exposed or independently of exposure. And 3, it is not an intermediate step on the causal pathway of the disease and outcome. If it were, it would be a mediator, not a confounder. Here is an example of the relationship between obesity and myocardial infarction, MI, or heart attack, and the role of cholesterol as a confounder. We know that obesity can be associated with cholesterol, primarily that those with obesity may have higher cholesterol levels. We also know that cholesterol can be associated with myocardial infarction regardless of whether or not people have obesity. And finally, cholesterol is not a necessary step in between the disease process of obesity leading to myocardial infarction. So cholesterol level could be a potential confounder for the relationship between obesity and MI. Because confounding can distort the true association between our variables, we want to be sure to control for it. We can do this in design with randomization, restriction, and matching methods, and in analysis with stratification and modeling. In design, we can use randomization, when appropriate, to evenly distribute known and unknown confounders between study groups. You do need the resources to conduct randomization and a sufficient sample size for an even distribution. We can also restrict our study to only people who have one level of the confounder. For example, we might only include people with low cholesterol in a study examining obesity and heart attack, or only include women in order to measure an association that we believe may differ for men and women, and most do. We can also match exposed and unexposed, or cases and controls, on a confounding characteristic. Pair matching results in one-to-one matches between individuals in a study group, and frequency matching results in the same distribution of a characteristic between groups. In both restriction and matching, while these are straightforward ways to deal with confounding, it may reduce the number of eligible participants for the study. And they may also reduce the generalizability of your study results if your study participants are very restricted or homogeneous or don't match the population at large. In analysis, we can use stratification to observe the association of interest at each level of the confounder. To do this, we collect the potential confounder information, then stratify our data by exposure to the confounder or level of the confounder, and assess the measures of association of our exposure and outcome by each level of the confounder. This is a good way to separate variables that are confounders, meaning they have an effect on the relationship, but the effect on the measure of association is mild, from those that are effect modifiers or modifiers, in which the relationship between your exposure and outcome may differ dramatically by levels of the modifier. Stratification can provide excellent information on the intricacies of the data and is important to do when you believe a relationship may differ by levels of a third variable, like gender, age, or socioeconomic status. The beauty of statistical modeling is that it allows us to include multiple variables in an analysis that may be distorting the relationship of interest. For variables that have little confounding effect, it is appropriate to control for them in a model by standardizing their influence across the population. But this can hide the effect of effect modifiers, such as some socioeconomic determinants, so it is important to assess variables for interaction and modification before controlling for them in analysis. You can conduct more sophisticated modeling as well that allows for determination of partial probabilities or propensity scores or cofactors in your analysis of the relationship of interest. And we'll cover more of this in Module 7. To summarize confounding, assess your study for potential confounders, control for confounding in design as much as possible, and then control for confounding in analysis. Finally, in our steps of assessing causal associations, we ask whether the association we found likely is to be due to chance. Statistical inference is when we use data to say something or make an inference with some confidence about a whole population based on the study of only a few, or the sample. It's very rare that an investigator can evaluate every member of an entire population, so we have to make this inference based on a sample. If we repeat our study over and over again with a new sample each time, results from each sample would be different. This is sampling variability and is the random error that creates the possibility that our estimate will differ from the true estimate simply because of variation in the samples. We use statistical inference to estimate the likelihood that our association is not due to chance, and we do this through hypothesis testing and by placing our estimate in a range of likely values, or the confidence interval. We'll cover how to do this in topic 6.6, but know that increasing our sample size helps to increase the probability that our association is not due to chance. Our next step is to move to stage 2 and apply guidelines for causal inference to our association. Criteria for causality provide a way of reaching judgments on the likelihood of an association being causal. The Hill criteria were established as guidelines for this, but not all need to be or should be applied to every study. The most important criteria to apply is that of temporality. Any claim of causality must involve the cause preceding, in time, the presumed effect. Without temporality, we cannot make a statement of causality. This is why experiments in which the researcher can manipulate the exposure provide the best evidence of causality, closely followed by observational cohort studies. The strength of association between the exposure and outcome can provide some evidence for causality, as the larger the effect size, the greater likelihood the relationship is causal. A dose-response relationship or gradient, in which increasing the dose of an exposure leads to an increase in the outcome, also provides some evidence for causality, but isn't required, as some exposures have a threshold they must reach before leading to an outcome. Consistency means that the association has been found in different populations under different circumstances by different investigators. The greater the consistency, the more evidence for a causal association. Less important factors include specificity of association, which means that a single exposure should cause a single disease, but this criteria, along with analogy, are not really valid or are weak criteria that we don't use anymore. Plausibility and coherence essentially mean that the relationship makes sense in the context of history and biology of the disease. And experimental evidence is not always possible, but it means that evidence from a laboratory or animal experiments or from randomized control trials can greatly enhance our understanding of causality. So these 4 criteria in red are the most important for assessing causality, and temporality is the only criteria that scientists all agree on. Causal inference is not a simple or a quick process, and no single study is sufficient in establishing causal inference. It requires judgment and interpretation, and consideration of the weight of the evidence supporting the causal relationship of your association. You cannot prove causal associations, but you can infer it from the evidence. In summary, association does not necessarily equal causation, but you can apply the steps in this topic to determine causal inference. Applying the stages includes assessing for bias, confounding, and chance, and you can prioritize and apply causal criteria to your association to infer causality. Final thoughts. Improving your ability to assess causality begins in study, design, and planning. The best way to be able to infer causality is by designing your study to be free from bias and confounding, and to have the statistical power necessary to detect effects and to conclude that your results are not due to chance. Thank you.